Hello, everyone. So if you remember back to 2.1, remember we were looking at two problems. So the first one was finding the slope of a tangent line, and the second was the problem of finding the instantaneous velocity. And remember that in both cases, we had to do a similar kind of computation. We were looking at the change in the output of a function divided by the change in the input. And then we had to let some number approach some other number or some point approach some other point. So basically, we were using limits, even though at the time we didn't really realize that. And now that we've briefly studied limits, we're in a position to come back and understand both of these problems and define derivatives. And derivatives are basically the process that we were doing in 2.1. So let's go ahead and get started. So let's define derivatives. So we have to assume that our function is going to be defined close to a and at the point a, so both of those. And then we make this computation. So the derivative of f at a is called, if it exists, it's called f prime of a, and it's given by this formula. So we look at f of a plus h minus f of a divided by h. We compute it, see what we get, and then we take the limit as h goes to 0. And because h is going to 0, we get some number that depends on a, doesn't depend on h. That's called f prime of a. So this is called the derivative of the function at a, if it exists. Or equivalently, if you were to replace h by x minus a, you could check that you can also rewrite it as f prime of a as the limit as x tends to a of f of x minus f of a divided by x minus a. Okay, so derivatives are hugely important. They have lots of applications in lots of areas of mathematics, but the definition by itself hopefully is not too painful. So derivatives are very useful for finding rates of change in lots of different scenarios. So we've seen two of those already back in 2.1. So if y equals f of x was a curve that we were thinking of, the graph of the curve, then this computation f prime of a gave us the slope of the tangent line, right? Because P was at point A comma f of A, and then we looked at a nearby point Q, which was A plus H comma f of A plus H, we could write it. And then we looked at the change in Y divided by change in X, that was the slope of the line joining P to Q. And then we had to let Q get closer and closer to P, which was essentially taking H closer and closer to 0. So there it was the slope of a tangent line. Or if f of t is the position of a particle, then you could check, go back to the calculation we already did, that f prime of t is the instantaneous velocity at a given time. So we've already seen two applications of this, but there are many, many applications. So for a while, we're going to be studying derivatives. How do we compute them? What do we mean by derivatives? What are the applications of derivatives? These are going to be basically half of calculus, understanding derivatives. So let's look at some examples. And quite often I'm asked, I have the definition of derivative. It looks kind of complicated and I have to take a limit. But, maybe I've done some calculus before and or maybe I've seen, something online or whatever, and I've seen all these rules for computing derivatives. So the derivative of x squared, will let us see is 2x and so on. Why don't I just jump in and use all those rules instead of thinking about the definition? And I have maybe a few answers. Well, maybe the main one for you is that you could be asked to compute the derivative using this definition for some simple examples in an exam. Okay, but that's not really a satisfying answer for me. But I mean, maybe the best answer is, all these rules work great if you're in one very particular or a few particular situations, which is when your rules apply. But if you face, some unknown example where you can't use any of your rules, maybe it's a different function that you've never seen before and you want to try to compute the derivative, if you can't use those rules, the only thing you can do is go back to the definition. And if you've never thought about the definition, then you don't really have anything that you can do. So understanding the definition gives you better tools and it gives you a better understanding. Okay, so let's do two examples. So here is one where, if you've seen all these tools, if not, don't worry about it. But if you have, you could jump in and use those and you would get the answer probably faster than I'm going to do right now. But let's see how the definition works. So let's find the derivative of x squared plus 2x minus 1 at any number a. So let's fix a number a and try to compute f prime of a. And okay, what do we do? Well, we use the definition, right? The only thing we can do is use the definition. So we have to look at the limit as h goes to 0 of f of a plus h minus f of a divided by h, right? The limit of this expression on the left. And I didn't do anything yet, right? That's just the definition. So whenever I want to compute a limit by or a derivative, using the definition, we have to look at the limit of this object on the left. So what I'm going to do is look at this object and then try to simplify it and then take the limit at the very end, because if I start off by writing limit of this, then I have to copy limit onto every single line. So let's just start with this, and then afterwards we'll take the limit at the very end. Okay, so f of a plus h minus f of a divided by h is a great start. But then, okay, what function are we actually using? So we have to write that in our function. So x squared plus 2x minus 1. Okay, remember we compute f of a plus h by replacing everywhere the x in the formula by a plus h. So here is f of a plus h. We just replaced all the x's by a plus h. And then similarly, f of a we compute by replacing x by a in the formula. So this is the same thing we started with. We just subbed it into our particular function. And next, basically, the only thing we can do is to expand out the brackets, right? And remember the cross terms. For instance, a plus h squared expanded will be a squared plus 2ah plus h squared. Similarly, we multiply everything out. You have to be careful on this formula with the minus sign. So minus f of a. So there was minus a squared plus 2a minus 1. When we expand that, we get minus a squared minus 2a plus 1. So always, if you're computing the derivative using the definition, be very careful with the putting in a parenthesis on the minus f of a if you need to. Okay, and then the good news is that we get a lot of cancellations. So in the problems you'd be given where you have to compute the derivative using the limit definition, normally you would find cancellations. So here I see an a squared, I see a minus a squared, 2a minus 2a, minus 1 plus 1. All those terms are going to go away. On the top, we're just left with 2ah plus h squared plus 2h. And now everything is divisible by h. So we can divide top and bottom by h. We just get 2a plus h plus 2. And then remember what we were trying to do. So now we've simplified it. We have to let h go to 0. Okay, but 2a is just fixed, right? A was a fixed number. It doesn't pay attention to h. The h is going to 0, so this piece is going to go to 0. And then there is 2, which is also just a fixed number. So as h goes to 0, this is going to go to 2a plus 2. Okay, so great. So we managed to compute the limit of f of a plus h minus f of a divided by h. That's f prime of a, right? So we computed f prime of a is, in this case, 2a plus 2. And if you've seen those other rules that I'm referring to, you would say, okay, f prime of x is 2x plus 2, using the power rule, the sum rule, and so on. And that's great. So later we'll talk about those rules. But make sure that you're also able to compute simple examples like this using the limit definition in case you're asked. Okay, here's an example, for instance, where to compute the derivative, we need to go back to the definition, where you cannot use the rules that we talked about. And I tried to make this example as simple as possible. There are way more involved examples. But okay, let's say f of x is x squared if x is bigger or equal to 0, and f of x is 0 if x is less than 0. Is our function differentiable at 0? And you could maybe try to wing it using the rules, but really they don't apply in this case. And there are more complicated examples that I could make if I really wanted to. So with this example, we really have to go back to the definition of derivative. Okay, so we can't use standard results. So what was the definition? The definition was, right, f prime of a is the limit as h goes to 0, f of a plus h minus f of a divided by h. In this case, we're interested in a equals 0. So we have to look at f of 0 plus h minus f of 0 divided by h. And okay, we know that f of 0 is 0 if we sub in. So we have to look at f of h divided by h and try to take the limit. And now we have a function which is different in two different cases, right? F is equal to x squared if x is bigger or equal to 0, and it's equal to 0 if x is less than 0. And we said when we have functions defined like this, where we have two different cases on the side of whatever point we're interested in, we should look at one-sided limits. So let's consider if h is bigger than 0, then f of h is going to be in the land of h squared. So we're going to get h squared divided by h. We get just h when we cancel, which goes to 0 as h goes to 0. And then, okay, if h is less than 0, then we have to use the other formula. If h is less than 0, then f of h equals 0. So we're going to get 0, which of course tends to 0. Okay, so we computed both the one-sided limits, right? So the right-sided limit and the left-sided limit agree, and they're equal to 0. So the two-sided limit must be equal to 0. So now we've managed to compute the limit as h goes to 0 of this expression. So we've managed to compute the derivative, right? So f prime of 0 does exist, and it equals 0. So in this example, we really needed to use the definition of the derivative using limits. So do be prepared to use that, even if you've seen these other rules that we're going to talk about later. Okay, I know, for instance, I know many rules on derivatives, but still I've written a few papers where I have to go back to the definition of the derivative. If you want to do something really fine that isn't just a rehash of stuff that already exists, then you really have to use the definition. So the definition is a reasonable thing to know and be able to use. Okay, what about physical interpretation? So we already said, these two particular examples we looked at, it's finding the slope of a curve. it's finding the instantaneous velocity of a particle. What about, more generally? So this is going to be a little bit vague because I'm trying to have something that applies to many different situations. So let's suppose we have some quantity y, which depends on some other quantity x according to the equation y equals f of x. So, there is an input, there is some output. I produce some number of units of some quantity, say widgets, and y is the amount of profit that I make, or it could be anything basically. X is the square footage of a house, y is how much it would rent for, or how much it would sell for. There are many inputs and many outputs that we might be interested in. Okay, then the average rate of change of y with respect to x is just the change in y divided by the change in x, so over an interval. So f of x2 minus f of x1 divided by x2 minus x1. And then the instantaneous rate of change of y with respect to x when x equals a is f prime of a, which we just talked about. So these are two different rates of change. So the average rate of change over an interval, or the instantaneous rate of change at a point in time. And then, okay, if these are supposed to be physical quantities, then they probably come with units. So, if you're doing physics, I know they care a lot, or maybe engineering also, they care a lot about what are the units. So what would the units for this be? Well, based on the computation, it should be the units for y divided by the units for x. So the units for the derivative are units for y divided by units for x. And okay, that makes sense, right? If we think back to our examples with velocity, if f represented a position in meters and x represented, time in seconds, then the units for the derivative, which were a velocity, were meters per second, right? So units for the output divided by units for the input, meters per second. So this makes sense, okay? So in general, the derivative is the instantaneous rate of change. So let's see a simple example based on this. Suppose, I don't know, some company produces fabric of a fixed width, so the only thing that's changing is how much fabric or what is the length of the fabric they produce. And let's assume that the cost of producing, x yards in length is C equals f of x dollars. So C for cost, and x is the length of fabric we produce. Okay, then what are the, what is the significance of the different things that we talked about? So f prime of x, which is the instantaneous rate of change of cost with respect to width, that's the rate of change of the cost with respect to the number of yards produced. Right, so if f prime of x is very large, then the production cost is increasing very quickly. If f prime of x is very small, the production cost is increasing only a little as we produce more and more yards. And okay, the dollars, what are the units? Well, we said the units for the derivative should be the units for the output divided by the units for the input. So the input is in yards, the output is in dollars, so the units for f prime should be dollars per yard, right? Output divided by the input. Okay, here is an equation, for instance, f prime of 1,000 equals 9. What does that mean? Well, it means that when we've produced 1,000 yards of fabric, the rate of change of the cost is equal to 9. So in other words, after 1,000 yards are produced, the production cost is increasing at a rate of $9 per yard. Okay, and I claim that we might expect that f prime of 500 is less than f prime of 50. So why would we expect that? Well, f prime of 500 is the rate of change of cost after we've produced 500 yards. And f prime of 50 is the rate of change of cost after we've produced 50 yards. And we might expect, if we've already produced 500 yards, if we produce, another yard of fabric, then it's not going to cost as much as producing another yard of fabric if we've only produced 50 yards, right? Initially, producing more is going to cost quite a bit, but then eventually, if after you produced a lot of fabric, adding a little bit is not going to cost too much at all. So this is, I guess, so-called production efficiencies. The more you produce, the less it costs you to add on a little bit more. Okay, so this was a very simple example, just giving an idea of why derivatives are important. Now, we're not going to go too much into this in the class, but hopefully you'll see way more examples in engineering and physics and other subjects that you're doing. Basically, whenever you're studying rates of change, whenever something is changing, then chances are derivatives could be important. So I hope you'll find them useful and interesting. Okay, so in the next topic, we'll look at how to compute derivatives, rules for computing derivatives, and so on. Thanks, everyone.